Thank you for the introduction. My name is Javier Hernández, and I'm doing the PhD thesis at University of Salamanca. So I'm going to talk about quantum dynamics of spin forbidden peroxidation catalyzed by the DpgC enzyme. So the main goal of this study is just to understand how this enzyme is able to catalyze the peroxidation of DPA in absence of any cofactor, metallic or mechanical. So for this study, it has been widely studied during the last 20 years, but these studies are normally focused on the biological part. So in this case, I focus just in this step of the mechanism, just the addition of molecular oxygen. So just to try to know in detail the reaction mechanism, we try to analyze the influence of the spin-off decoupling. And why the spin-off decoupling? Well, as you all know, generally most of the organic substrate are singlet in its ground state, meanwhile the molecular oxygen is a triplet. So this reaction should go to an intersystem crossing that, well, between the two lowest states, triplet and the singlet, that should be slow at room temperature due to the following the non-relativist quantum theory. Then if the right side, I try to represent what I've done. That is, I propagate a quantum wave packet, starting in the singlet, then it is able to cross the intersystem crossing due to the spin-off decoupling, and the wave packet can be divided into the two states, the singlet and the triplet, and in the case if the wave packet reaches the singlet state, it can reach the minimum and the product formation. So in this case, as I explained, spin-off decoupling are considered, so the crossing between the potential surfaces and the product formation is allowed. Going into the computational details, for the electronic structure, 6 singlets and 1 triple potential surfaces, along with their spin-off decoupling, were computed, but using a reduced dimensionality system, in which I withdraw the tension ring and also the tensile A. I follow the last studies of my group that test different fragments and methods and basis set. So this approximation is studied considering 2 dimensions, the distance between the alpha carbon and the molecular oxygen, and the torsional direction, the molecular oxygen. Then, as I said before, just this approach is studied using quantum dynamics. Okay, so as you all know, because Sandra told before and also Mari, just to study the dynamics, we have to solve the time-dependent Rodríguez equation, and for that we use the multi-conformational time-dependent Hartree method as implemented in quantum software. So we express the wave function as a set of time-dependent simple particle functions that are in turn expanded via time-independent primitive basis. Starting with the results, here we have the singlet and the triplet states. Then the triplet state is purely repulsive, while the singlet states show 3 different minima at the more or less the same distance and 3 different angles. So here we have the intersystem crossing between the 2 potential surfaces. So we assume that the superoxide formation can be associated with this intersystem crossing and the magnitude of the spin-off decoupling. I don't represent it, but in this intersystem crossing zone, the spin-off decoupling is around 80 centimeters. Besides, as I said before, 5 singlets cited states were calculated also. So for that, we use 4 approaches for the wave packet propagations. So the first one is the lowest spin-orbit state that corresponds with the lowest eigenvalue in the matrix. So it corresponds with this part of the singlet and this part of the triplet. Then in this case, in this potential, I don't consider the spin-off decoupling, just these 2 parts of the states, the 2-state system, where I consider the singlet but also the triplet, just one of the components of the spin-orbit coupling matrix, and then I just do the average for the calculations. Then the other approach is the four-state system, the same singlet, and just the three components included in the matrix, and the seven-state system that includes the whole picture, that the six starter state, the six singlet state, and the triplet, including the three components. Starting with the quantum dynamics results, the first step is to obtain the reaction probability, that we obtain it from the flux that we measure after the intersystem crossing, when we reach the minimum, and that corresponds to it. We did it for different total angular momenta, and we observed that when the wave packet has more, it is above the barrier, the probability starts to increase. And in this case, for the spin-orbit state, the probability is quite higher. Then, when I represent the multi-state approaches, in this case, it is considerably lower due to that I not only focus on the shape of the potential, but I have also the spin-orbit coupling, so the probability is quite low. Then from the probability, we calculate the integral section. So for that, we calculate the propagation for different total angular momenta from 0 to 100 under the collision energies. So in the case of the spin-orbit state, the thing that I try to study is that for energies that are slightly below the barrier, 0.6, 0.7 electron volts, the wave packet reaches the minimum. So probably we should do a further analysis, because probably there are some tunneling or something like that. The case of the multi-state approaches, the 2 and 4 state approach is practically the same here, but in the case of the 7-state approach, this trend, when it reaches the barrier, changes. So we suppose that it goes probably because this other singlet state play a role in the dynamics. And if we compute the thermal rate constant, we observe the same in the case of the multi-state approaches. So we have they are practically the same, but the 7-state system rate is a little slightly higher. And in the case of the spin-orbit state rate, we keep the same proportion along the temperature, about 1,000 higher. Then just the conclusions, you can say that the spin-orbit coupling allows the wave packet to reach the minimum, and the peroxide formation, that the thermal rate constant have been calculated for this dimensionality system, and using MCPH approach, and that the 7-state approach differs probably due to that the spin-orbit coupling is considered, that the other 5 singlets play a role. And the next step that will be just to compare this thermal rate constant and this with other frameworks such as the transition state. And finally, I would like to acknowledge my group in Salamanca, especially my PhD supervisor, Cristina Sanz and Susana Gomez, and the organizer for the opportunity just to give this talk. And thank you all of you for your attention.
Thank you very much, Javier. Is there any questions?
Yes, so thank you very much for the talk. So I have a couple of questions. So regarding the spin orbit coupling, so you're talking about the spin versus the angular momentum of the O2.
Yes.
But at the same time, why not consider spin rotation of the O2? Because the O2, the nuclei can also rotate.
Yes.
And then the question about this is that, to my understanding, usually spin orbit it's a relativistic effect. So usually it's significant in very heavy nuclei. So my question is, do you have some intuition of like why it's significant here? So these are the questions.
We consider just to study the spin-off decoupling because there is no reason, because normally an enzymatic peroxidation of this kind, for example, not DpgC enzyme, but other deoxygenase enzyme uses a metallic cofactor that is the one that has a high spin-off decoupling. So, despite that we have a low spin-off decoupling, maybe it's one of the reasons that this reaction could be possible. And
Spin rotation. So I would
Yeah,
imagine
yeah,
that
the-
spin
yeah,
rotation
yeah,
would also be larger if you
Yeah.
model.
the thing is that I just use these two dimensions for let's calculate the potential, but I in the previous studies of my group, the one that I indicated before, they also optimize the geometry. I have, let's say, the zeta matrix of the optimized just for each. So it allows the molecule just to the molecular oxygen just to move during this reoptimization. I don't know if
Okay, but maybe it has something to do also with giving the ground rotation statement. Okay, thank you.
Thank you. Jason.
I was just going to comment on the question of a small coupling or spin orbit couplings in organic molecules still being important. I think one needs to consider the time scales. So if the molecule is able to stay in this region of slow spin orbit, small spin orbit coupling for a long time, eventually it will change. So I think that's the kind of the missing argument. It's not just about the magnitude, but also how complex the molecule. If there's no competing churn, that is able to drag the molecule away.
Thank you for this comment. Any more questions? Okay, let's thank the speaker again. Thank you.